we already looked at, we talked about polar earlier when we talked about cylindrical coordinates, right? Cylindrical coordinates are polar plus the z-axis. So they're polar in 3D. So we've actually talked about this stuff, so I'm not going to beat this part to death. But remember, when we want to use polar is when we have a region that is symmetric around the origin, something that's circular. Okay, so we have our polar transformations. All right, so you're going to want to know those because that's how you transfer an integral into polar. And we'll take a look at an example here in a little bit. And we don't need to do that because you guys have already had some practice with that. But these are the kind of regions that would indicate we'd want to use polar. If you got something in the XY plane that is circular, polar might be good. But here, if you have something like this where it's a disk, you'll definitely want to use polar because this would be ours just going from 4 to 6. To do this in this one in rectangular is a mess. This one in rectangular is not so bad, but it may be hard to solve by hand. All right, so we'll look at that here in just a second. So, and you saw the stuff in the video. Basically, what we're doing with polar is it makes some integrals easier to deal with. So we need to decide when we want to do that. Well, like we said, when the region is circular, all you need are your transformations. X is r cosine theta, y is r sine theta, and x squared plus y squared equals r squared. Those three things. And then there's the dA component, and you saw this in the video, so I won't bore you with it again. But the dA, which is like the dx dy or the dy dx, when we convert to polar, because the way the region is set up, it's like a cut off slice of a pie. We're actually using the arc length of that piece. Well, arc length is the radius times the angle it subtends. So that puts an extra r in our dA when we go to integrate. Okay, and it's just because we're doing the arc length. So we have our transformations. If you have any x's in there, it's r cosine theta. Any y's in there, it's r sine theta. And if you have an x squared plus y squared, it's r squared. We do not want to have x's and y's in there if we're integrating with respect to polar, because we're integrating with respect to r and theta. And the dA is either going to be r dr d theta or r d theta dr. What you want to take from this is if you're doing the integral, if you're converting to polar, remember to put an extra r in your integrand. Otherwise, it won't come out right. Okay, that's really what's going on with polar. So let's take a look at an example. I'm going to do this one here. Let's do the second one. The volume under the plane z equals x above the disk of radius 3 bounded by x greater than or equal to 0. And we'll look at it both in rectangular and polar so we can decide what we like better. Okay, so x is greater than or equal to 0. So we're only looking at the right-hand side of the circle. And let's talk about it in rectangular first. Now we're looking under the plane z equals x, right? So the function is just x. So it's going to be a double integral, and then x, and then we got to decide if we want to do dx first or if we want to do dy first. Now, if you want to calculate this one by hand, you're going to want to do dx. You're going to want to integrate, excuse me, with respect to y first. And I'll show you why. If we think about this region here, part of a circle, well, we know that the equation of a whole circle is x squared plus y squared, in this case, equals 9, or 3 squared. This is going to be something you're going to get really used to in these next couple of sections. Is we're going to have a lot of regions that are circular or spherical, so get really used to dealing with these equations. So I want to integrate with respect to y first, and it's because of that extra x. So if I integrate with respect to y first, that means I'm solving this for y. So y equals plus or minus square root of 9 minus x squared. Okay, minus for the bottom half. So that part right there is the y equals negative square root of 9 minus x squared. That'll give us the negative y values. This guy here is going to be y equals square root of 9 minus x squared. So those are our limits. Negative square root of 9 minus x squared up to square root of 9 minus x squared. Okay, because we're going from this curve to this curve. Inside limits can be in terms of one variable. The outside limits have to be constants. Well, now we're just going to integrate with respect to x, and we're going to go there, which is 0, 0. Very nice. Okay. Now, this is actually a doable integral by hand. So let's go ahead and do it for practice. So we integrate with respect to y. So 0 to 3, x times y, and y is going to go from negative square root of 9 minus x squared to square root of 9 minus x squared. And then we'll integrate with respect to x. That's okay. You know, we can put an x in there. We're going to integrate with respect to x still. Fundamental theorem, upper minus lower, right? So basically what we're going to have 0 to 3, x, we're going to have this minus this. Well, we're subtracting a negative. So we're going to end up with 2 times the square root of 9 minus x squared. That's from the fundamental theorem of calculus. Okay, kind of combined a couple steps there just because I know I'm going to run out of room if I don't. Okay. Here's why we can actually still do this one, because the function was x. And without that x, this is still doable, but you have to do it as area under the curve. Now we can do it as a u sub. So u equals x squared, du equals 2x dx. All right, there's my 2x dx. Actually, let's have u be 9 minus x squared. Might as well get that all in there, which will bring in a negative, not a big deal. So we do need a negative. So now we have a negative 2x dx. So we have negative the interval from 0 to 3 of square root of u. So u to the 1/2 du. Oh, and actually, let's do this too. I'm a big fan of changing the limits on u substitution. So when this was a 0, put in 0 for x, you get 9 minus 0. So the lower limit is 9, the upper limit will come out to be 0 when you plug it 3 in. That way we don't have to sub back. I'm a big fan of changing the limits, you don't have to. All right, antiderivative is, so we get negative 2/3 u to the 3/2 from 9 to 0. So first part's going to be 0 minus a negative. So minus negative 2/3, 9 to the 3/2. All right. That's the square root of 9, which is 3, cubed, which is 27, times 2/3, which is 18. Okay. This one's doable by hand. I mean, I chose a function, so it would be. Okay, that's in rectangular. That's the kind of stuff we were doing last week. Now let's talk about doing it in polar. All right, so in polar, the nice thing about polar is it handles circles very easily. Okay, because all we have to do is take into account, okay, the radius goes from 0 to 3, and the angle goes from negative pi over 2 to pi over 2. So 0 to 3, negative pi over 2 to pi over 2, and we could actually switch that order if we wanted to, because they're both constants. Now, let's talk about what goes inside. Well, there's an X in there that has to be transformed. Remember, X is R cosine theta. So we get an R cosine theta, and that came from the X, right? That was the X from there. Now this part, this is that dA we were talking about. That's where we have to put in the extra R. So R, and I'm doing dr d theta. So that's that extra R that you have to put in when you integrate in polar. Okay, it is just part of this. And now we get to calculate. Now we've got the R times R, so that would be an R squared. So the antiderivative of that, so we're going to have negative pi over 2 to pi over 2. So again, kind of combining two steps. We're going to have R cubed over 3 cosine theta, because that's a constant with respect to R. And then R is going from 0 to 3. And then we'll still integrate with respect to theta. So I can put the 3 in. 3 cubed again is 27. Divided by 3 is 9. Let's pull the 9 out. So basically now we're just down to this 9 from negative pi over 2 to pi over 2 of cosine theta d theta. Antiderivative of cosine is sine. Let's got the 9. So 9 sine theta, negative pi over 2 to pi over 2, 9. So we'll have sine of pi over 2 minus sine of negative pi over 2. So 1 minus a negative 1 is 2 times 9, and there's 18. Same thing either way. You know, we can debate which of those was easier to do. But as you can imagine, because when we do rectangular coordinates, anytime there's a circle, it's going to involve a radical of the radius squared minus the variable. In general, polar will be easier. This one would have worked out okay. It worked out nice because we had the extra X in there, so we could do a U sub. Would have worked out okay because we were doing from 0 to 3. But if we didn't have, if our function was something different, or we were not doing a nice symmetric interval, this thing would have been kind of messy.